introduce Ramaswamy a little bit, and at the same time do a little teaching about precisely what this IPCC thing is. They shared the Nobel Prize with Al Gore, and that is the focus of this series. It is a worldwide study group that produces reports. As far as I know, doesn't pay anybody involved except the small secretariat. And the jobs have decidedly different levels of time commitment. And the largest unpaid job, if I'm not mistaken, is the job of convening lead author, CLA. Now, what is a CLA? Well, Ramaswamy has been a CLA. This is the table of contents of the AR4. The first one was called FAR and then SAR and then TAR. But to get to fourth, you'd have to say FAR again, or FOAR, something. So they use the number, fourth assessment report. They're roughly in 5-year cycles. And there are 3 components, as most of you know: science, impacts, and mitigation. So this is the table of contents of the fourth assessment report, Science, Work Group 1. And it has 1,000 pages nearly, several big chapters, as well as on the front end, always, in all of these, a summary for policy makers and a technical summary. So the second of the mainstream chapters is called Changes in Atmospheric Constituents and Radiative Forcing. This is a summary of what we know, and in particular what we learned since the last assessment report. And its title page identifies 2, normally it is 2, convening lead authors. And Ramaswamy was the convening lead author. This is a heroic job. And not only, you can see from the international composition of the lead authors, the LAs, that's one tier down, that it is a very international group, chosen for their specializations and also for international diversity, and a review process and outcomes, as you saw, a 100-page chapter. Now, I don't want to spend much time introducing Ramaswamy, except to say that he's been at GFDL for about 20 years. He got his doctorate in SUNY Albany, and is an expert on radiative forcing and the radiative transfer of energy within the atmosphere. A wonderful subspecialty full of physics, chemistry, math, applied math, numerical methods, you name it. Ramaswamy has had to be a master of a number of fields to be the kind of expert he is. And he will be reflecting both on his field and on the GFDL process in a talk entitled Evolution of Climate Science and the IPCC Assessments, Understanding the 20th Century Climate Change. Thank you all for coming.
Thank you, Rob. Can you hear me? Thank you, Rob. That was very kind of you. Made me think that working for IPCC is so great. But you know, the IPCC process itself, what I have to say, there's so many people involved that, you know, I think not everyone does get recognition for this, but there's actually a tremendous number of people involved in the process. Whether as people who write the chapters, or people who review the chapters, or people then, you know, give really harsh scrutiny of the writing. It is really a very sobering process, but you know, the interesting thing is one learns a lot from it. And as I actually through the process, and I've been sort of doing this in an insane manner for the last 15 years. Okay, I thought that in my talk I'd maybe have some fun, this being the 4:30 talk. You can't do all the science, so I thought I'd front load this with some very basic questions. Is there a pointer here? All right. So I thought that I would front load the talk with some basic question of how did IPCC come to be? I mean, it got sprung up in 1990, the first report, but what was the sort of process that led to it? And I just thought I would mention a little bit of the history as I have read about it, and it's definitely skewed towards what I have read, so it may not contain everything that is really part and parcel of the process. But nonetheless, I need to give you a flavor of some of the major things that happen to actually lead to this concept of IPCC, and namely the international coordination on climate research and assessment. So to begin with, and I don't want to go back to prehistory, but pre-1950, weather was always the main concern. Climate was, not necessarily, by climate I mean, like, let's say, it changes over time periods of decades and longer. It was not really a principal concern. And it was mainly goaded by observational issues, like how can we get observations over Europe or over Australia. And so it was partly scientific curiosity and the need to understand the global weather away from where I live. But also there's a good deal of national interest in geopolitics, which becomes clear when you see sort of declarations by heads of states in different countries about how important weather prediction was, but in reality they really wanted to know more about terrains and coordinates of other places very well. In World War II, for example, there's this famous thing about the Normandy landing. The German army was not expecting it because the weather was supposed to be really bad. But the weather forecasters actually found days and breaks in the storms, and it was a kind of surprise thing in the battlefield. And then there's a later story about President Truman asking for Russian data, actually demanding Russian data from Siberian stations because they wanted to know the weather of Japan for a winter attack. Never happened because of the surrender, but nevertheless weather data played an important role. And then in 1919, IUGG came into being, which is it's an organization that a lot of us are part of. And this eventually became a major part of the International Council of Scientific Unions. And then, following the World Meteorological Convention held in Washington in 1947, WMO was formed. So it's sort of more than 50 years old. Then in the 50s, you'll see that I'm mentioning some names. I'm not mentioning all names, but some names, because it turned out that there were some people through the course of this history who were not just scientists, but they were also brilliant administrators and very powerful diplomats. So they could actually persuade, goad, cajole, they could do everything and get things accomplished. And one of the people, such person as Harry Wexler, who was chief of the US Weather Bureau, and he actually is responsible for, almost singly responsible for persuading governments to fund the International Geophysical year in 1957-58, which of course started the heating measurements of carbon dioxide. And also later on in the decade, there were permanent scientific bases set up in the Antarctic, ice drilling began in Greenland, and of course, there's also the launch of satellites, Sputnik first and the American satellites, which were partly weather related. But the focus still remained on weather through all this. And then the IGY actually spurred an Academy report in '61, which actually said there were large data gaps, for example, no data south of 30 south, something like that, and excepting over Australia. And this spurred action by WMO to really have routine balloon measurements of the temperature, etc., and which was called the World Weather Watch. But still no governmental awareness on climate, although climate modeling had started to get underway, particularly with the GFDL operations then located in Washington. Then in the 60s, ICSU and WMO came together to form GOD. And mainly this was for weather forecasting, but Bert Boleyn, again another very influential person internationally, who started actually as a weather forecaster, but soon turned his attention to geochemistry. And with the steadily rising CO2 curve, he began to highlight climate, which actually now started to become part of meetings at the WMO. And then there was a SCOPE report, Scientific Committee on Problems of the Environment, which was published by ICSU. Then there was a meeting of global effects of environmental pollution in Dallas in 1968, in which Fred Singer was one of the conveners of an important session on the changing atmosphere. Then there was a month-long meeting which led to the SCEP report from MIT, which was actually a very famous landmark. It turned out it was exclusively US scientists. I didn't know about this till I read. It was actually mainly US scientists. So Bert Boleyn then organized a SMIC report in Stockholm in 1971, which was multinational. There were 14 nations, including some heads of states. I don't know, Indira Gandhi actually went to that particular meeting. Then in the 60s, GFDL moved to Princeton. And I later sort of see how GFDL's director was influential too in some of the international activities. And simultaneously, NCAR was formed in Boulder under Walter Robertson's guidance. Now, the above reports, so we're talking about the early 70s, did not lead to any specific consensus amongst the scientists. Some scientists talked about greenhouse gases and warming of the earth. Some were talking about pollution from particles, cooling it. So there was sort of, and I guess the art of coming to an assessment or evaluation or consensus statement was not there for them. But one thing was recognized in that in both the SMIC and SCEP reports that human-induced emissions could cause climate to shift dangerously. That's how the phrase I took verbatim from the report. In the 70s, you had a lot of weather-related catastrophes around the globe, famine, storms, etc. And Bob White, another famous influential personality, chief of the US Weather Bureau, later chief of NOAA, he was also instrumental in setting up GFDL in Washington. He pushed for international cooperation in climate research, which actually helped launch the GATE program, which was sort of the first comprehensive multi-nation campaign to understand atmospheric physics and dynamics, including convection, in the Atlantic region. Then after that, there's a workshop on climate issues in '78, but scientists still did not know what else to do but just write reports about their individual research. The assessment area was just still not there. In fact, some scientists in 1978 were asked, what do you think government should do with this report? And they said, read it. They should read it. So then the journalist asked, so after that what? Well, they should read it again. So, it's a bit crazy. I didn't really know where they wanted to go. Then, you can see some of the events kind of accelerating a bit. There was the first World Climate Conference in Geneva in '79, which actually led to the formation of formation of WCRP, World Climate Research Program. And the first head of the WCRP Joint Scientific Committee was Smagorinsky, who was, of course, the first GFDL director. And this was formed to actually lead worldwide climate research. It was housed in WMO, it actually still is in WMO, but the idea is not to do weather, but to do climate. Now we come to the 80s. And 80s were truly, you can call a revolution, at least in the social structure of climate science. There were a succession of meetings in Austria, starting in 1980, which were actually annual meetings. And then there was a very famous Charney report led by Julie Charney in 1980 from the Academy. And both that report and the 85 meeting in Villach actually produced some of the first substantive results, which really laid the steps towards IPCC. So there was data from the paleo records of CO2 and temperatures. There were the first supercomputer models, the coupled climate models by Suki and Kirk, and then observations starting to hint a temperature rise for the first time since the dip in the late 40s and 50s. And Bert Boleyn here actually started to really stir things up and took on issues with an urgency, and actually managed to convince both scientists and government administrators that indeed was time to take on a wholesome look at climate. IGBP was formed as actually as a rival to WCRP because there was still the notion that WCRP was doing too much of weather. So Geosphere Biosphere program came because they wanted to actually look at longer timescales of biogeochemical interactions. And of course, by this time, the ozone story was going on, the science and then the regulations leading to controls, especially the Montreal Protocol. And the climate people then tried to arrange a similar thing in '88 called the Toronto Conference on the Changing Atmosphere. It attracted a lot of publicity, but it kind of didn't sort of meandered into sort of nowhere after that. And then, of course, in '88 there was a severe summer in the US, and simultaneously Margaret Thatcher's push for worldwide coordination and prediction of climate. And these sort of accelerated things, and which led to the formation of the IPCC 1988. And just as a sort of piece of trivia, the very first meeting trying to structure the science of IPCC, the Working Group 1, was actually held in GFDL. It was in the seminar room. A handful of people. Suki was there, Kirk was there, and of course Jerry Vaughan was there, who was the director there. And then all the people who you see Working Group 1 as names, they were all there, huddling together and laying the groundwork for the Working Group 1, the first Working Group 1 report. So then WMO and UNEP created this organization called IPCC. It was designed to be a hybrid organization because the feeling was that existing international organizations were too much either scientific or too much governmental. And this is supposed to be neither really, but also to be that, both of them together simultaneously. And the idea was that they should sum up the state of these art knowledge about the climate system with projections for the future. And it should consist of scientists doing rigorous science, but it was also charged with delivering a consensus summation of the assessment in a manner that was understandable to policymakers, because it's felt the previous reports had kind of fallen short on that score. And of course, the rest, as they say, is history. First IPCC report was published in 1990, which actually was in preparation for the Second World Climate Conference held in 1990, which in turn led to the Rio Summit in 1992. All right, so coming to the Intergovernmental Panel on Climate Change in general, this is because governments require information on climate change. The function is to provide assessments. Scientific community contributes widely, as Rob mentioned, on a voluntary basis. And there were a lot of new authors in, for example, the latest IPCC, so it really draws in new authors in every section of IPCC, although some people hang on, like myself. And the substance of the IPCC report is actually in the hands of scientists. It's actually amazing how it works, although there are policy knowledgeable people involved, but still it is really in the hands of scientists. And in terms of the fourth assessment, just for some statistics, IPCC assesses published research. It's sort of a little bit of a misnomer that IPCC does its own research. No, that was the idea of creating IPCC. But it better not do its own research, it just assess research. And each assessment goes to multiple reviews, revision, re-review over a period of years. So AR4, for example, had a 0th order draft in which each chapter was commented upon by 6 to 12 friendly experts, which then laid the ground for the 1st order draft, which was reviewed by about 600 reviewers, then which led to the 2nd order draft, which was re-reviewed by about 600 experts again, worldwide, and by dozens of governments. And then government comments were invited on the revised summary for policymakers in late 2006. And then overall, it's about 3,000 comments that were received in the concept of working with one. And 30,000, sorry. Correct. Thank you, it's 30,000. 3,100 for one chapter, probably. And it's important to know that by the time you go through this process, the assessment conclusions cannot be the views of a single scientist, no matter how hard that scientist tried. It just can't be. It reflects really a much broader process. And the working group one, I think Rob already said this, 150 authors, 450 contributors, 30,000 plus review comments, and then 11 chapters in working group one, frequently asked questions, about 5,000 literature references, about 1,000 pages. All right, what am I going to do next? Well, I think, let me see how much time I really have, but I want to run through an evolution in the knowledge really on the following topics, which is by no means exhaustive. I just sort of picked and selected a few items through the various assessments. So atmospheric composition, and then that leads to radiative forcing of the climate system, and then model simulation of responses to these forcings, what were the observed changes in climate at these different points in the assessments, and what is the attribution of the various observed changes. So the very first thing is almost becomes a homage here to look at the paleo data on CO2. So this is CO2 going back through various glacials and interglacials, and you see that last blip here, which is the steep rise in the industrial era. And it's sort of now much more than sort of anything that you had within the last interglacial. And of course, this means that it's a new forcing on the Earth as we know it, and the increase, of course, are mainly due to fossil fuel burning, and CO2 has never been as high at least more than 500,000 years. Then, just juxtaposing that in the current era with the other gases, you have CO2, methane, nitrous oxide, and the sort of big panels show the rise over the last 10,000 years, and the inset shows it over the last 150 years, and last 200 years, sorry, and you see the steep increase for all of them. A little bit less so for nitrous oxide, but you see it for all these gases. So, and these are unprecedented increases that have happened. And these are now coming from paleo records, from proxy records, where it's a very consistent story that's being told by these observations. Now methane, this methane over the last 20, 25 years And I wanted to show this because there's a story in methane which we don't understand completely, which is that methane, and if you look at the top part, which is sort of the increase in, which is the concentration of methane over the last 20 years, and you see that it sort of has a very strange thing. It's not rising all the time. Sometimes it has flattened out. It's now actually flat, or at least to 2005. And it's sort of curious that the budgets for methane are difficult to do, and it's still not clear as to why this is so. It's not as traceable as CO2 increases are in terms of the various sources of this gas. Then there are, of course, the halocarbons, which are long-lived gases, again, human-induced emissions. And these, over the last, between the period 79 to about 90, were kept on increasing, particularly CFC 12 and 11. Then the Montreal Protocol came into place, and you see the flattening out of 11, 12, methyl chloroform. You have flattening out of a lot of things, 113, 22. But some of the gases, which are really long-lived, are still rising. SF6, it's very low concentration. The concentration is on this graph here, on this axis here. It's still very low, but it's still increasing. And SF6, molecule to molecule, is about 5,000 times at least more strongly absorbing than CO2. It's just not good that it's actually present in very low concentration, but it is rising. And then there are some of these replacement compounds which are now beginning to rise because they are the ones that are substituted for the chlorofluorocarbons. And then, just to sort of illustrate why these gases actually do what they do, it's actually quite illustrated to go back to the sort of radiation that provides a balance for the Earth's climate, in the incoming solar radiation and the Earth's effective black body emission in the long wave, and the balance between the two actually helps establish the net radiative balance of the planet. And then below that, especially in the panels which are sort of colored and labeled as methane and nitrous oxide, etc., you see the absorption bands of the various gases in distinct parts of the electromagnetic spectrum, going from UV, visible, near infrared, and then far infrared. And for water vapor, you see, for example, it has so many bands from the far infrared, very strongly absorbing bands. For CO2, you have this very famous 15 micron band, but also some additional bands which are strongly absorbing. But basically, the presence of these bands actually helps them to behave like greenhouse gas, traps radiation. And one other thing to note, which I'll mention, which I'll amplify on later in the context of aerosols, is that in the solar spectrum, you see that there are no gases really. The vast part of the spectrum, which is very large insulation coming in, there's actually no gaseous absorber, which is actually present. So all that radiation actually comes to the surface in the absence of clouds, of course. But if you have aerosols present, they get to interact with a lot of quanta. And that's the reason why even a little bit of aerosol is actually so effective in terms of its effect on the climate system. Now, just sort of going into a little bit into this the CO2 question, one of the things that happens with CO2 is that the increase in CO2, the forcing goes roughly as a logarithm of the increase in CO2. And the reason is because the CO2 band is actually the main band, 15 micron band, which is this band here. So this is a plot which, this one shows the outgoing long wave radiation as a function of spectrum in the infrared. This shows the absorption band of CO2, and you see that this 15 micron band is very, very strong. And so for the current amount of CO2, it's actually saturated at the center. So there's nothing more can happen. You can keep adding CO2, but that particular point is not going to absorb more. But what happens is the wings of the band, these portions actually now start to play a role because they can impede the outgoing radiation from going out. And that's why when you do, for example, a change due to increasing carbon dioxide, in this case from 1980 to 1990 values, you see that at the center, actually nothing happens. It's the wings of the bands that you actually get this absorption. And it goes as a logarithm of the increase. It's sort of a very hip pocket rule. Whereas for methane, it goes as a square root of the increase. And for halocarbons, the forcing goes linear, which is one of the reasons why there was a greenhouse tinged issue with the protocols, with the Montreal Protocol, because these CFCs, if they continue to increase, the estimate was that by 2025, they would have been at least 3/4 of the CO2 forcing, because their forcing is much, much stronger per molecule than CO2. All right, so let's now go into the various IPCCs and see how they dealt with this radiative forcing. So this computation of what is a forcing, which means literally if you change the concentration from pre-industrial to present, what is the change in the amount of energy trapped? So this was the first attempt, IPCC 1990, did just the gases really, did the quantification of the gases, and they arrived at this number. It's currently a pretty robust number. It has never been a challenge, it's been improved upon. Then after the first assessment, which really focused only on the well-materials gases, there were two other things which came online for the next assessment in terms of radiative forcing. One was ozone, stratospheric ozone. And what you're seeing in this plot is when the temperatures get cold in the Antarctic, this is the Antarctic, this is height versus ozone amount. And when the temperatures get cold, the ozone just goes from here to here, just zeroes out completely because of the CFCs depleting it. And that leads to a forcing, a negative forcing, which I'll show in a couple of slides later. But that was one issue which came up after 1990. The other one that came up was aerosols. And basically, this was something which was known, but was not really quantified at the time of the 1990 report. So this is the situation in all our megacities, the amount of particulate matter that there is. And what was actually, the aerosols do is they can scatter radiation, they can either scatter radiation or they can absorb radiation, depending on what the matter of the aerosol is. And that leads to warming of the column. And it can also affect clouds, which again I'll come to later. So these two then were the modifications introduced in the 1995 report. And you see that the diagram became slightly better. People would now try to put bars, error bars. So that was an improvement in the 1995 SAR, the second assessment report. Stratospheric ozone appeared, and then aerosol components were actually quantified for the first time. And then came, so this was mainly sulfate aerosol, which actually grew out of work by Charlson and Leobi and a couple of other authors in the University of Washington. Then black carbon was just trying to get realized by the time of this report. It really came into full being in the third assessment report, where it was realized that the fossil fuel black carbon emissions were just soaring after the 1950s. And then this was quantified in the third assessment report, which led to the even more beautiful diagram, which was, had color bars now. And also, carbon from fossil fuel burning was actually partitioned with black carbon and organic carbon. And there were better quantification estimates. But there was one thing which always eluded, and you'll see even in both the second and third assessment report, namely this effect of aerosol interacting with clouds, just couldn't be quantified because of the inherent uncertainties involving clouds. Well, so now we come post-third assessment. Now in this case, two things happened. One is the observation got better, mainly through satellite observations, so you can actually see the globe. And this is a picture from a satellite, from the MODIS satellite, showing the aerosol optical depth. You see the plumes, for example, coming from Sahara. You also see big plumes over Asia. And also models became better. They could do transport better. One of the problems with modeling aerosols is its inherent spatial heterogeneity and temporal homogeneity. And that problem really complicates the decalibration. But if you could pin down various processes affecting it, you actually get better models, and that's what happened. And this led to an improved estimate of the direct radiative forcing. Now the aerosol cloud interaction, in a very simple term, just works like this. It's the aerosols condense, the water condenses on aerosols to form clouds, but then if there's more aerosols, then there's more competition for water vapor, and so the drops get smaller for the same amount of liquid water available. They get smaller, which means that the clouds become thick, the cloud drops become smaller, which means they get more reflective. When they get smaller, they don't precipitate out so quickly, so the two effects add to really give a big reflection of the cloud, increases the lifetime of the cloud, increases the albedo of the cloud, the reflection property. There are lots of other things also which come out in the aerosol cloud interactions, but it still remains one of the poorly understood processes regarding the radiative forcing. But nevertheless, some progress was made as a result of models, and we come to the estimates of where that led to. Let me just get briefly to the other forcings. I haven't mentioned solar so far. The solar has actually come down in estimate from the earlier previous assessments to actually only about a tenth of a watt per square meter. It's actually less than half of what was quoted in the third assessment. Basically based on better models, better use of the proxy data, better reevaluation of sun like stars, but it still actually comes from only one state. And that's really still a limitation in terms of confidence in this particular forcing. Of course, we won't know ever what it was in, since 1860 to now, but nevertheless, there is still uncertainty about it because we don't have enough data. Another forcing is due to volcanoes, which Isaac talked about last time. And in the case of volcanoes, the eruptions are episodic, and only from very explosive eruptions you have particles going into the stratosphere where they live for about 1 years. And so we've had a lot of volcanoes in the past, although there's been a period in the 20 and 60 when there were no volcanoes. And then there are these three big ones, the Agung, the El Chichon, and the Kubu. And so, but these are episodic. So here we come to the summary of the fourth assessment report. And again, clever idea, they just rotated the diagram at 90 degrees. So that's ingenuity at its best. And you see that, so the aerosol was actually quantified for the first time. You actually see now an uncertainty bar for the indirect effect, which actually helped them to quantify the total anthropogenic forcing. Though the uncertainty bar is still large, but it actually was quantified. Then you had, of course, the well-being greenhouse gases, which have always been very accurate. They just keep increasing because of the increase in concentrations. And solar was another highlight, namely it was evaluated to half the value of the previous assessment. So it actually made the anthropogenic factors even more highlighted. But for the first time, it was actually possible to quantify the best estimate for the total anthropogenic forcing, something which the previous three assessments couldn't do because of limitations on the knowledge available. But in this assessment, it was actually possible to do that with a large uncertainty range, 0.6 to 2.4, but nevertheless, to the two things possible. It was greater than 0 and it was substantial. All right. So basically now just going to response from these forcings. I just want to touch upon that briefly. These are the kind of models that we use. There's a climate system that we're trying to describe. These are how the globe is divided into grid points. And this is what we are seeking to do in the climate model, combine land, sea ice, and the atmosphere. And just sort of, again, as a historical note, this is how things actually began in terms of climate model. And people like Suki began with the atmosphere, then they went on to combining atmosphere and land, then they went on to play ocean and sea ice. Then came the 90s when sulfate aerosol was introduced, and then in present day there are some models with some degree of carbon cycling, and then now the latest in the early 2000s is where the atmospheric chemistry is actually coupled with the rest of the climate system to make it truly interactive, and then looking beyond that is the Earth system model, which you'll hear about probably in the next talk by Ron. Okay, so now going back to a little bit of chronological order as to how these assessments saw things. So through 1990, this is kind of the first assessment. This is a temperature record that they saw. It stops at about 91. And so what did they do with that? Well, the main finding was that the broad overview of climate change was given, science was given, there was a discussion on uncertainties, and a mild evidence was provided for the warming of the climate system. Then after that, in the second assessment, you see the surface temperature outside. This is a global annual mean surface temperature that I'm showing. And you see that with years, now it's kind of rising. And then this is the first attempt, and done in the second assessment report, where a model with only CO2 and well-mixed gases included versus one where aerosols were also included showed that you could get a large cooling from the amount of aerosol forcing that was figured out, that you could actually get a cooling. Although there was no direct comparison done with observations, all that the second assessment said was it was very consistent with the observation of the warming, because the warming was offset slightly with the sulfate aerosols. Then the second assessment actually went on to do a very interesting thing called fingerprinting pattern. And basically it was the following, that this is actually a study which was spearheaded by Ed Santer. You took the various components which have perturbed the system, well-mixed greenhouse gases, sulfate aerosol, volcanic aerosols, stratospheric and tropospheric ozone changes, solar irradiance, and you ask what is the fingerprint of this particular forcing onto the atmospheric temperature. So this is what you get. You get warming throughout the atmosphere with just the mixed greenhouse gases, with a bit of cooling in the stratosphere, that's called CO2 cooling. With aerosols, you get a cooling everywhere in the atmosphere and surface. With stratospheric and tropospheric ozone, the stratospheric ozone cools the stratosphere because you lose a greenhouse gas, and the tropospheric ozone increases warm the troposphere. Solar irradiance increases warm the troposphere, volcanic aerosols cool the troposphere, but will warm the stratosphere because the aerosol particles behave like an absorber there. And if you add all the forcings, this is what you get. You get a warming at the surface, a bigger warming aloft, which Isaac explained to you last time, and then the cooling in the stratosphere. So what this assessment did actually was to then compare the result of such a fingerprinting of the atmospheric temperature change with observations. So the observations are at the bottom here. And the top is the calculation with just the well-mixed greenhouse gases. And this is for a 25-year period, roughly the 70s to the 90s, which is the data that is available for the entire atmosphere. And then the middle panel is one with aerosols included. So you see that the sharp warming, the warming is sharply reduced because of the aerosols and becomes actually cooling. And then in the stratosphere, you have an ozone effect. And so the statement that was made in the second assessment was the balance of evidence suggests a discernible human influence on global climate, which is a landmark statement based on actually mostly this particular analysis. Then after that came the third assessment, and now sort of the warming is, more perceptible. That's the rise in the last 20 years. And one of the sort of points made in the third assessment was that the variability, and this is 3 different models showing unforced variability. Basically, you force the model with nothing, and then watch what the atmosphere ocean ice interactions do. And the highly central model, the GFDL model, and the Hamburg model, they all show these variations. On the right, you see the observed temperature change since the last 100 years. And the conclusion was that none of these models in that 1,000-year run could ever reproduce this kind of increase that occurred. So in other words, natural variability due to the coupled system just cannot explain the observed temperature change. And then this was sort of another landmark and key result in the third assessment report. Namely, if you now run a model with your best estimate of the forcings, then and the observations are in red. So if with natural forcing only, you actually don't get it. In the last 25 years, you actually get a cooling instead of a sharp warming here. With anthropogenic forcing only, you actually do get that in the last 25 years, but there's a bit of a mismatch in this period around 1950. But you put the two together, and you get sort of this very good agreement. But it was based on one model. And so, but it did lead to this conclusion that most of the warming of the past 50 years is likely, in IPCC parlance means 66% level of chance, to be attributable to human activities. And that was again sort of thing that took the whole attribution thing forward from the 1995 report. So now we come to AR4, some of the AR4 results, and now this is the temperature record, which of course now extends up to 2004 in this case. And so you see all this rapid increase, including some of the warmest years. And we have contention about one of them, but nevertheless, at least the warmest 11 years can be reported. And so basically the trend has continued. And now the attribution studies have gone, actually, have started to include more models with different kinds of representation of forcings. And what you now see, analogous to the previous curve in the third assessment, this is now observations in black, and then the red sort of spaghetti type looking thing is actually all the model runs that were submitted to IPCC, and different ensembles runs too, starting from different initial conditions. And again, basically natural forcings don't explain it, but natural plus anthropogenic forcings actually explain this quite nicely. Okay, and that was on the, now one thing that AR4 took it forward to was the direction of global, not only global temperature change, but continental temperature changes. And so one of the conclusions reached was that it's likely discernible. Notice that for global, it's very likely in terms of confidence level now, but on continental scale, it's still likely, it's still 6%. And basically, like in the global case, you see on every continent the natural forcing, which is in blue. That response doesn't explain the observed increase, but the combined natural plus anthropogenic actually explains the very very nicely. And now I just focus on, when it comes to uncertainties too, everything is not a bed of roses here. This is the GFDL model, so that this was one of the models which was submitted, which was shown, which was part of that spaghetti diagram in the previous slide. And it's the same kind of thing here. You see the observations. The gray envelope is the models, a measure of models variability, basically starting from different initial conditions. You apply the same forcings, you get a spread, and that's that spread. And then you see the natural, which is sort of going like this, can't explain the observation. Anthropogenic, which is sort of going, which is blue, and then red is the combined. And obviously there is pretty good agreement with the observation. Now, one of the things I've been saying is the aerosol cloud interaction, which is sort of the indirect effect, is still not completely understood. In fact, one of the pure secret, but now it's a very open secret, if you read the document carefully, is that most of the models did not have the indirect effect in their models when they ran for the simulations. Okay, the indirect effect number is a large negative. If you recall, the forcing diagram is a large negative. So it does have an effect. And so we've actually run with one estimate of the indirect effect of the aerosol cloud interactions with the same model as you're seeing the results here. And what you get with that is something like this. So what you're seeing now is, in the red, is the same result that you saw before, which obviously falls right dead in the middle of the auto. It matches the observations pretty well. And but then if you add this indirect effect, which, as you can guess, lowers the temperature, and so actually does bring in a bit of a discordance with the record, with the observed record. But this is still a poorly understood process. There are lots of facets. This is only one facet that we've managed to represent so far, and there's still work going on in all the centers about this. How is this process to be represented and modeled? The stratosphere is actually pretty well explained. This is sort of, again, one result which happens to be from the GFDL model, that if you put in the observed, if you consider observed changes in gases, greenhouse gases, ozone, volcanoes, everything, you actually match the observation, in this case the MSU channel 4 temperature anomalies, pretty well with the model considering all the forces. And this then permits you to look at how the model, in this case the GFDL model, has evolved with time in terms of height, in terms of the variations of height. And so you see, as you come into the 20th century, you are warming, and the troposphere actually warms more than the surface. The stratosphere, though, has started to cool way back in 1900 due to CO2 increase. In fact, only about 10% of CO2 increase was needed to actually register what you call a human imprint on the stratosphere. And that's then continued. And only in the last 25 years, of course, the ozone depletion has accelerated that cooling signature of the stratosphere. Okay, some other climate variables. This is, again, coming up in the observational data. The snow cover and Arctic sea ice are both decreasing, and they've decreased, and they've actually not been successfully explained yet by models, because models don't really have sometimes all the processes needed to do this. But nevertheless, that is, again, sort of leads to this picture of a warming world without any ambiguity. Now, what's in the pipeline? What can come in the future? One of the interesting calculations done in AR4 was this commitment calculation. Namely, if you held the composition, atmosphere composition constant, what would you get? You would get an additional warming because of the inertia of the system. And that additional warming is 0.6 degrees centigrade with CO2, or equivalent CO2, equilibrating at about 400 ppm. Then there are these other scenarios. A1B is kind of the one that most people look at in terms of sort of a middle of the road scenario, and you see that by 2100 it's 2.8 degrees centigrade warming, and with a CO2 equivalent of 850. So more emissions means more warming, and even if you don't increase anything, it's still there's a commitment of half a degree centigrade warming in the system. Other things happening in a hotter world. Observational sea level rise show that sea level rise is, in the 20th century was about 6 inches of change, mostly from expansion of hot water. And of course, and this is estimates from the past, 1870 or so, then through the 20th century, instrumental record, and then this is sort of where the projections will lead to, and you'll hear more about this in non-stop. Okay, finally I want to turn to precipitation. I've been talking about temperature. So what about precipitation? So this is the data from precipitation. You saw one, I think one sort of a flavor of it, one perspective of it from Isaac's talk. This is actually what's happening to precipitation. It's increasing over some areas, but it's also decreasing over other areas. And so that's the sort of causes for these individual locations is still to be determined in the modeling domain, in the models. And if you actually look at what the precipitation looks like in the model, so the same model which does reproduce the observed surface temperature increase, when you look at the land precip here, which is plotted here, you see the problem in attribution of precip. The noise is so great. The gray envelope is just the noise because of the different slightly different initial values. And this actually inhibits any kind of sort of trend determination, first of all, in the observations, and any kind of attribution too. Although there are some people who claim that UChannel variations actually can be represented well in their models. Anyway, so this is a problem with precepts. I don't want to leave you with the idea that everything has been necessarily solved. So this is my final slide, and I just sort of summarize the key points that are now emerging from the latest assessment, and in a sense, these have evolved through the various assessments to come forth now very strongly. Definitely an unprecedented rise in the long-lived greenhouse gases, and particularly greenhouse gases, 20% increase in CO2 over the last 10 years, and this is driving climate change in a big way. And there is no question about the warming of the climate system. Lots of different parameters just from the observation record are indicating a warming over, let's say, a 20-year period. And in terms of global mean temperature, this is very likely, which is sort of a 90% confidence level, is due to anthropogenic greenhouse gas increases. And all the projections from the models indicate that this is going to warm further, the climate is going to warm further, and that it's very likely that there will be larger changes than observed in the 20th century. And with the increased warming, you would sort of really get a higher signal to noise, and which would lead to higher confidence in the projected patterns of warming. Okay, I'll stop there and take questions. Thank you for your attention.
Questions for our speaker?
It looked like in your map of precipitation change, you didn't have a plot from Australia, but it looked like it was greener.
That's all.
Yeah, it's a big drought, right?
Yeah, but you know
The drought more in the southeast.
Yeah.
this is green, right? This is yeah, this is not, I don't know if it's capturing the recent one, this overall essentially scale increase. I don't know, I have to look into that.
Could you comment any more about solar forcing, and if it's, there was a recent article in Physics Today this month commenting on solar forcing as a possible role, and you had a small error bar on it in the recent report. Is that a fairly robust, I mean, and we should just consider the solar forcing idea to be an outlier of significance?
Let me get to a slide before I answer. Okay, so this is sort of the summary of the forcing. So you're talking the small bar here. But you know, the other thing you have to look at, which I didn't in sort of speeding through this, I didn't mention it, but you have to look at what is called the level of scientific understanding. And low means 2 in 10 chance that that's correct. So it indicates, and compared to the high that you have for greenhouse gas, which is like a 9 in 10 chance, and medium is like 5 in 10. So comparing to the high, you know, we really don't understand. That's why the low symbol is there. These estimates really come from what's available. So the available evaluations, you know, just suggest this. I mean, people speculate higher values, but the problem is that they're not due to direct irradiance. They come about once they start doing indirect things like coupling it to chemistry, or coupling it to ozone change, coupling it to some kind of feedback. Then, yes, you could get bigger effects, but the problem with solar in the overall sense is that if solar, let's say solar forcing was as big as a CO2 forcing, then you're going to be hard-pressed to explain what happened to the CO2, because we understand its physics pretty well. So that is frequently forgotten. I mean, there's a double whammy here. It's for any of these forcings, you can try to change values, but then you have to run a model and see how consistent you are in explaining the observed temperature change. That really will be the proof. And I don't know if these solar arguments are successfully doing that. But nevertheless, as I mentioned, this estimate from Jewish Green is really one step, one model. And so, you can, most of the other forcing estimates come from, quite a few models. In fact, the aerosol indirect forcing was given a bar only because there were several estimates available. So it is true that, there is that one handicap that we have only one model and we don't have data going back. And that's sort of a distinctive disadvantage. So, but that's why there's a low confidence.
Ron, while you're on that slide, since there are different studies that are coming up with estimates for the different forcings, how are they combined to give you the error bar on the total? Where does that come from?
This one?
Yeah.
Well, you actually do PDFs, all these. This is the way it was done. You do the PDF for each forcing. So obviously the spread is narrow for the well-mixed gases, it's very large for the aerosols. You just assume a normal distribution. And you do that, well, for the aerosols it was not. For aerosols the log log because of students. And so I think I might have the result from the PDFs. But anyway, that's how you do it. You construct the PDFs and I can show you later on. No, sorry, I can't find it. But basically, there's a PDF for everything excepting log normal distribution of everything excepting log normal for the aerosols. And then you do a Monte Carlo calculation through that to arrive at the final value. So, but the mean is pretty much close to what you get just from a sort of root mean square sum. Was that a question?
Current connectors talk with the Rodebaker argument. We aren't getting smarter in any fundamental way. You've shown us a lot of increase in understanding over a 15-year period. Maybe one way to ask the question is, what will be in the fifth assessment report, and maybe in the sixth and seventh, that isn't here, and will, in fact, we begin to be aware of, or more sure that we aren't on, a very high time sensitivity?
Well, I mean, clearly one of the issues is the clouds, whether it's related to aerosols or just as a pure feedback mechanism in a climate system. It is definitely one of the things that is that has to be high on in terms of being able to address key issues in the next assessment. Will we? That's up in the air. I mean, next assessment may not be enough because I think most people already know what kind of principal things for the next assessment because they're working on it. But maybe 10 years from now, maybe there'll be some issue with clouds if we have increased more resolution, more data. It may actually help to constrain. It may not, there may still be a lot of uncertainty, but if you can understand where the uncertainty is coming from, that would be a big step. I think that is possible to achieve.
So is the cloud legal with error bar summarizing what we really don't know?
Well, remember, the attachment to get the confidence which is low, which means that of the processes that are represented in the models, this is what you get. That doesn't mean that you capture necessarily all the processes or you necessarily being able to capture all the significant processes. There may still be something there. In fact, there is something there. So far, all these estimates are really for interactions with water clouds, mostly. In most models, it's the interaction with water clouds. With ice clouds, we have some fundamental gaps. We don't even understand how nucleation occurs in the free atmosphere involving ice. There are different pathways. Which pathway functions when is still not fully understood. And then the whole glaciation process, when does an ice cloud start to precipitate, is much less understood than it is for water clouds. So this large negative which I showed is a bit of a distraction because it actually really takes you away from the observed record somewhat. It could be offset by the interaction with ice clouds. Some people have actually done that, but there is no, the reliability is still to be cheap on that score. So the whole topic of aerosol interaction with clouds, and plus the cloud feedback itself, is a very, very major issue, major outstanding issue.
What do we want to ask of that? So let's put that into the context of, can we truly expect to get so smart that we know what kind of planet we live on before it happens to us, or we trapped in some
well, I think
fundamental problem of uncertainty?
in an absolute sense, it is very pessimistic. But I think the question is going to be got to only in stages. You're going to have to do this in steps, small steps to the question. I think in one stroke it is not really possible to say, do we know what the climate sensitivity is? Once you understand clouds, hopefully, and assuming that there are no gaps in the other processes, we can proceed ahead. But I don't think it's going to be done in one fell swoop. It's going to have to be done in stages where you start to maybe address things like water clouds first. Why stratiform clouds, and so La Nina conditions. Why do they look the way they do? Because different models actually simulate them differently. They may all get the global temperature increase due to CO2, correct? It would be our observations. But still the response on these short time scales, so in La Nina may be different. So it might be something that is possible to get to in stages rather than in one big stroke. It may not be possible to get in one big stroke. And there is pessimism about whether we actually get to that. But I think, considering where we are 20 years from, hence from all the dilemma about clouds in the 80s, sure, one pessimism is that, we're still talking about clouds. But the other aspect is that we have gotten a lot of data, and a lot of intelligent know-how on clouds. So maybe we haven't grown smarter, but we are less foolish.
Does that mean we've gone backwards on methane?
I don't know. Maybe Arlene can answer that. She's on the expert on methane. Have we gone backward on methane?
Well, the fact that it's flattening.
The flatten out. The methane curve is the concept of flattening.
I think it's not very well understood why it's flattened.
We were happy when it was increasing the population and counting, et cetera, and now that it's flat, like what?
Yeah, I think it's more to do with the sources, right?
Right, I was going to say, part of the problem with methane is that the source, sectoral distribution is not very well understood. I think there are a general total emission of methane, but the partitioning also of national versus academic.
Another question from Zoe.
Yes, I was wondering if you could briefly address the role of the ocean in the thermal analysis.
Role of the ocean in the 20th century?
I'm sorry?
The role of the ocean in the 20th century climate?
Yes, in the climate system.
Right. I didn't have a chance to really give a look at a lot of the oceans, but the oceans are warming. The rate of warming is a bit of an issue because there is still the ocean heat content data is still being worked on, so it's still lacking a definitive quantifiable answer, but it is warming. There's no question, and the heat is going to the ocean, which is being reproduced by a lot of models. I unfortunately don't have it to show that, but yeah.
You spoke about how the IPCC process evolved since over the last four reports, and as one of the few people who was really there at the beginning. Do you feel that as we've had this evolution in our understanding of climate, has our audience evolved as well? And can you comment on who's receiving this information and how well it's being received as it's changed over time?
Oh yes, I mean, absolutely. It's advanced and people are more receptive. I think even the appreciation for the process has grown a lot. And I think the appreciation for the reliability of the results has also grown. You see sort of still some fundamental points being challenged, which is right, because everything is not being addressed. But overall, some of the issues which were there, let's say 15 years ago, 10 years ago, no longer surface, at least not with that kind of intensity. Water feedback is one. It's really the 10 years of research involving observations, models, careful examination of various processes. I think has narrowed the uncertainty in water feedback. It hasn't on clouds, but it has narrowed the uncertainty in water feedback. So that's a big plus. Then the whole business of being able to quantify the forcing, the net anthropogenic forcing, that's a big improvement. And then the data, observation data now covers so many variables. So and the whole data length has increased. That's natural because as time goes on, you get more years of data. But that's a plus too. So all this has made the results more robust and reliable in the eyes of at least the people who receive them. And of course, AR4 has received exceptional visibility compared to, in my mind, previous assessments.
Can you go back to the slide where you have the evolution of the models?
It seems that the present day, the early 2006 editions, the 2000 editions, and the present day models, the additions that were made, and these latest kind of modeling efforts, are kind of tying all the pieces that were added before. It seems that maybe the modeling results that are going to come in the future are going to be maybe more surprising than they have been based on past editions. And in fact, you're kind of now really starting to have some major interactions among the different
pieces.
Is that
definitely, no question. Now, the next season ones are going to have, they're going to call the Earth system model. They're no longer going to call it just a climate model. The Earth system model, where important biogeochemical cycle is actually going to be represented.
So is that likely to be a big addition to the next AR5?
Yes, definitely. GFDL is going through a process which you might hear next time from Ron about how the entire carbon cycle feedback process is going to be represented. And going beyond even carbon cycle, other cycles are also going to be there. People are contemplating nitrogen. People are trying to think of ecosystem as a whole, trying to represent it somehow. So, yeah, they're getting more and more, as Suki would like to say, complicated. But you have to remember that some of the fundamentals in the processes that are already there are actually also getting improved. It's not as if, it's not like there's a module there for land and then, just have to sort of attach it to another thing to make that complicated model. But no, the land, the individual components keep getting improved also. But it's true that newer and newer things are being added, only because the scientific issues are being directed towards that. People want to know what's going to happen to marine ecosystems, terrestrial ecosystems, and you got to start addressing that. There's a question back there.
Do you understand better the black carbon forcing?
No, that remains an uncertainty. That remains an important uncertainty, especially because, again, it's part of the aerosol species, so as such, there are these issues concerning transport and removal of aerosols that plague black carbon also. But in addition, black carbon is a very strong absorber. And so when it mixes with something like water or mixes with other aerosols, the net absorption of the entire species goes up. How much it is mixed is not known. There's no quantification of how much these aerosols are mixed, which would give a different perspective than the way we are quantifying it now. The expectation is that the uncertainty bar is going to cover that. But if you saw the chart, it says medium-low confidence for aerosols. And one of the reasons why it is still medium-low, we couldn't decide on whether it should be medium or low. The reviewers kept saying medium, we kept saying low, so we decided on medium-low as a new definition. That's the way IPCC works. You get to carve out your own definitions.
Do they know it's positive or not?
Yes, oh, that it is. That it is positive. I mean, there is no calculation which is suggesting it's negative. The only way it can be negative is, you know, if it does start with something to do clouds in a big way. But that's an indirect effect. You know, black carbon heats a cloud, dissipates it, and nothing happens to replace it. Then, yeah, you know, well, no, that would be heating too. What I'm saying, that's wrong. Yeah, because you know, if you remove the clouds, that's a heating of the system. So actually, there's no way that black carbon can really cool, unless it does something where it creates more clouds.
It's very high.
Why would that cool the system?
To cool the upper layers.
No, it will warm. It will warm the upper layer.
It will warm, but
yeah.
Cool the.
Yeah, but then you know convection takes over. That process cannot sustain itself very long. So I doubt if there's anything that's possible that can cool the system. Now, how much it warms is an open question. That's still uncertain.
You shared with us some of the scale of coordinating the hundreds of authors and reviewers. I'm wondering if you can share with us some of the challenges you've faced in the process and also some of the learning that's taken place in the last 15 years and how you deal with a growing group of scientists and the growing challenge.
Let me tell you the positives first. You learn a lot. I mean, I learned about disciplines other than my own through the IPCC, where you really get to interact with top-notch people who are leaders in their own field, like ice processing. I had no idea before AR4 about intricacies of ice dynamics and shelving and I know it comes for the first time. But you learn a lot because you interact with experts. Likewise, they learn a lot from interacting with you. So that's a positive side of it. One of the unfortunate things, unfortunate from a personal viewpoint, but fortunate really from the IPCC process is the reviews and the scrutiny is becoming increasingly demanding, very demanding. I mean, for each one of these review comments, you had to respond. There was no, you couldn't wave them away. You couldn't say number 121, 125, 173 are all similar, so I was not. You got to respond to each one of them. You couldn't write at least a no or a yes. You couldn't write foul language. You had to sort of say, because this is documented. Everything is documented at Harvard, in the Harvard Library. So it's going to be very interesting social research at some point when somebody looks at all these comments. But you have to carefully respond to each one of them because, of all the comments received, about 40% are really serious. You can't just ignore them. Maybe 20% you can wave them away by saying, no, it's not workable. But you have to respond to each one of them. And you have to respond, especially on the first and second round. We had 4 rounds. On the first and second round, you have to respond very carefully because they could bite you the third time. Because they could say, I told you this in the first round, you haven't corrected it. And we have review editors who are, very senior people in the field. And our chapter review editors were Terry Nakajima from Japan and Ramaswamy from Scripps. And so they were there to make sure that we did respond to the comments and not ignore them. So that's a very challenging process. So what I'm saying is that at some point, it becomes excruciating. Because some people will make the same comment again. You could reply to them, they will come back with the same thing. And then you say, this is not the way I got my paper through JGR, but that's unfortunately the IPCC process. You have to address it. So, you spend a good 4 or 5 years, 3-4 years of your life trying to be polite and negotiate. It's interesting, you learn a lot. You sometimes learn that viewpoints that you had going into the IPCC were incorrect or had a flaw. And then you come out actually better after the experience because, some more intelligent people who look at the same thing offer a perspective that is much better than what you went up with. So you learn a lot through the process, but, it's becoming a very hard one. I mean, I've been through it since the '92 when the supplementary assessment was there. It's becoming harder and harder because you have to deal with more and more reviewers. It's getting visibility. You know, that's the consequence of increased visibility. You get more attention, which means that people are looking at, you know, your words carefully. We had, in fact, people who were non-English natives telling us how to write our English, and they were correct. So you learn all these things. But it's an interesting process. I would, you know, really suggest everyone should do it once and given the opportunity. Once, maybe not. Once.
I hope this may be a little bit, not the same time, but with extreme climate change, they have this concept in Norway. They put on the island, Storpark Island, they're putting for seeds, they're putting how do people get to this island if there's extreme disaster, when it's an ice, it's way out there? The second thing is, if there is a huge climate change or doomsday, I'm not sure what they mean by doomsday scenario, but how do they get these seeds to regerminate? How do we get them to germinate in a climate that's all messed up?
Are you proposing that as a topic for AR 5? For the next assessment, are you proposing that as a topic to do research on?
Yeah, I'm just suggesting. It looks like a very intelligent, nice man. I just want to see what you think.
I take a broader perspective of your question, which is what is the frequency of extremes, which then affects some aspect of humankind. You know, this being one activity. How do you get to places? How do you get to places, or how do you retrieve something from somewhere given extremes in weather like severe storms, hurricanes, etc. So you need to know when they will occur, how often they will occur, and you need to know details on those. And those are actually just coming along in terms of evaluations from these models to figure out, you know, how often do you get extremes in, you know, snowstorm or extremes in some whatever climate variable you choose. And that part is still not fully addressed because we don't have the models going down to those details yet. But the analysis on those kind of variables has started. So to answer your question directly, you know, how can you get to this place where the seed vault is in extreme weather? You would hope that people would supply, the people who are interested in this venture, you would hope that the weather people or climate people would supply them with reliable data on how often this is going to happen from hopefully reliable model projections. We are just not there yet, not with that kind of data.
Is there one final question?
So you talked about this, the uncertainty of the aerosols. So what about the relative growth of anthropogenic aerosols and natural aerosols?
Oh, this is what anthropogenic aerosol I was talking about. Natural aerosol is presumed to be, you know, sea salt and dust. So actually there's a tiny anthropogenic contribution of dust that's estimated here, but this is all anthropogenic aerosol. So it's sulfate, black carbon, organic carbon from human influenced emissions.
So but if, from last talk said that, you know, dry regions get drier, wet regions get wetter. So dry regions get drier means there should be more natural
there's some more dust emissions. Yes, you touched upon something that I almost put a slide in, but I couldn't because of the time. But dust, and especially atmosphere-land surface interactions leading to either increase or decrease dust production is a very, very important component. It may have played a role in the 20th century climate. It may have played a role even in the Sahel effects, which you heard about last time. We just don't know. We know we have understanding of some of the processes involved in that phenomenon, but we don't know everything about it. But that's certainly a very important item which has not been considered yet. And there is active research going on how, for example, a drier land, you know, how if it entrains more dust, what will that dust do? And for example, in Sahel, did the dust then in the atmosphere cause additional climate changes, over and above what was happening due to desertification? So it's an important point. It's not being taken into account in the models.
I suspect we could go on another hour, and I think we should stop. So let's thank our speakers.